Okay. Um, yeah, it's 11:30. So I'll be taking your class today. So Dr. Rizk isn't here. I know you're all very sad from last evening, so I'll try to keep this easy as much as possible. I've been grading your exam two. The results look better than exam one. I've been as lenient as possible. Your results should be out by this weekend, depending upon if Dr. Risk has had time to look at the results and whatnot. Your attendance for this week should be up. The code is 7777, 4 sevens. So that's your attendance. And okay, so uh, if everyone's ready, today we'll be talking about cluster validity, like how do you analyze cluster results? What is the math behind it? What's up? 7777, 4 sevens. I'll be talking about some of the examples, like real life examples that I've faced and that I've seen of why we need to validate our cluster analysis. And a couple of the in-class problems that we'll do today will come up in your final exam. One of them, there are two in-class problems that we'll be solving today within this lecture, and at least one of them will be in your final exam. So keep an eye out. It's not very difficult, but you have to remember the formulas for what we're doing. So what is, let me move this. So today we'll be talking about, you already know what like clustering is, what supervised and unsupervised clustering is. So today what we'll be doing is, once you have created your clusters, how do we know that they're any good? How do we know that they make any sense at all? Because in real life, when you're performing cluster for a reason, so for some sort of downstream reason, whether you're in medicine, whether you're in prospecting, whether you're in ad business or whatever, you have to find out like what you're clustering and what is the result and what you're going to do about it. Right. So that's what it is. There are a few terms that relate to cluster, like how we analyze clusters. So I'm going to talk about those first. And before that, I'll point out some real life examples of what happens when you don't validate your clusters correctly. And after that, we'll divide this into two different bits. One, what we do for unsupervised clustering, and one, what we do for supervised clustering. So the silhouette coefficient, how we calculate that, there'll be an in-class problem on that, as well as supervised clustering. So purity, NMI, and the RAND index. And how do we calculate this? And there'll be in-class problems on those as well. First, let's look at why we need, what do we mean by analyzing two different clusters, right? So you know what clusters are. You plot some data point in some Cartesian plane, and then you try to figure out what that data is trying to tell you. So like, are there inherent groupings within that data itself that give out some sort of meaningful information? That's what clustering is. So like you get insight into what real world value that cluster is telling you. So that's what we need. That's why you do cluster analysis. And for the difference between unsupervised and supervised clustering is that you have a ground truth and you're comparing your clusters with a ground truth. So in unsupervised, you have nothing but the data, and you are seeing what kind of clusters are popping up in the data, and you're trying to figure out what that tells you about the real world. So, and for supervised, you obviously know what the ground truth is, trying to figure out if your model of whatever you're trying to model through this data, does that correspond to the real world? That's what it is. And obviously, any sort of clustering analysis, this is upstream of your whatever you are trying to do. So after you perform clustering, then your actual statistical analysis starts. So you take each of those individual clusters, and then you perform lots of different statistical analysis to figure out if those clusters make sense, if they're telling you something real, what is the consequence of that, so on and so on. So let's look at it. Let's look at an actual real life example. So you'll find this entire slide is on the website, but a couple of these slides that I'm showing right now are not up on the canvas right now because I added them last time. So I'll put them up later on Teams or on Canvas. So this is an example of why we need to analyze clusters, right? So this was done at the behest of winemaking companies in France. What they were trying to do is given a bunch of different types of wine samples across multiple regions across Europe, they were collecting data on various specific things, chemical properties, like it tells you taste profiles, growth condition, production methods, etc., etc. So what they were trying to do is figure out if there are certain conditions, certain underlying truths to how wine is made, that leads to better sales, that leads to better reviews, and so on and so forth. Right. So the initial results that they got when I'll explain what silhouette scores are later on, but obviously high closer to one means good and farther away from one means bad. So in this case, when they ran the very basic k-means clustering, they were getting silhouette scores of 0.81, which sounds very good, right? So that means their clustering thing was going well, so they could move on to their actual downstream results, like which wine sells better, why it sells better, which one people like, and so on and so forth. But when like actual wine experts looked at the results, they said that your results, your clusters make no sense at all. So like each of the clusters contain completely different types and vintages of wine. As it says, like cluster wine contains Bordeaux reds and Australian whites. I have no idea what any of the names mean because I've never drank wine. So your guess is as good as mine why that's bad and why that's good. But what comes up here is that like these clusters are mathematically accurate, but practically they're bad. So they don't correspond to reality. And the entire purpose of data science and the entire purpose of statistics is to take numbers that correspond to reality. So if that doesn't, if they're not matching up, I mean, something has gone really badly wrong. So why did this happen? So there are two papers, they're linked somewhere in the slide, which talk about why this was happening. So the two of the biggest things was that like alcohol content was numerically much, like the values of the alcohol content was much larger than the other features. So because one of these features was dominating all the other things, so like they were collecting lots of different data. So there are lots of different attributes that they were collecting, like chemical properties, taste profiles, growth condition, production method. But this alcohol content, this was dominating the entire clustering analysis results, right? And because of that, it was like the algorithm was giving alcohol the total alcohol content much bigger weight to that feature than the other features. So they had the entire data set itself was scaled but was not standardized. You know what scaling and standardization is. Um, and also another problem that comes up is called correlation blindness, where the validity indices that they used, I think they used brand index, and they also used mutualized information, not normalized. You will talk about normalized mutualized information later, but they were using something called mutual information, which is unnormalized NMI. And because of that, they were unable to see before the experts came along that the clusters were formed along a single dimension rather than the full multi-dimensional multi-attribute data set. And the silhouette coefficient, which was pretty high, like 0.81 is pretty good. We'll see why later. Was not working very well in this particular condition, right? Because it was giving high silhouette scores, but the actual things that they were clustering were pretty bad. So how did people fix this, and how would you fix this when you are dealing with like real world data where the clusters make no sense? Is that you need to work with domain experts, right? As data scientists or as computer scientists, we are kind of generalizers, right? We generalize. We work with all different kinds of fields. We work with very different types of people. and very different types of disciplines. So we need experts in individual disciplines to come along with us and to help us understand why our data looks good or looks bad. So they came along and did all these stuff that you see here. They helped us. They helped the authors of the original paper perform feature importance analysis. So they figure out like which of all these hundreds of features that they analyze, which of them are truly discriminated, which of these are truly able to pull out individual effects. They created compound variables. So like they were collecting acidity, they were collecting tannin levels individually. And so what they did was they came up with compound variables, or they came up with indices that combine different attributes, which gives better information and which better reflect like the ground truth of actually how people like how people identify with wine. And they also implemented some custom business metrics, and they created some like hybrid validation approach. Right. So these are all things. Silhouette scores are something you're going to learn. We're not going to do Davy Boolean because it's very subject specific, and not all fields need Davy Boolean metrics. But we are going to do silhouette scores. We're also going to talk about what rand indices are and what it means by expert classification. And we're going to talk about domain-specific metrics. Domain-specific metrics means some sort of clustering method that only works for wine, but won't work for if you're trying to cluster weather data, or if you're trying to cluster cancer cells or whatever. So all these different domains have different, very highly specific metrics. And you'll find some of these metrics pop up in, like, if you're working in Python or in R, you'll find they pop up in very specific libraries. Like astrophysical libraries have very specific metrics. Cancer libraries have very specific metrics. And those are going to come up when you're working on real world data, real life data. And those are usually created by the domain experts. These are domain specific metrics. So after all these adjustments, the silhouette scores decreased, so it became mathematically worse, but the clusters were now much more aligned with wine classification. So this is what the clusters look like full-bodied reds, crisp whites, medium-bodied mix. So these were like the actual clusters that the domain experts wanted. I have no idea what these mean. So again, your guess is as good as mine. Why this was good and why these were bad. Again, blind tests. So like actual real world blind tests confirmed like each of the cluster members from different clusters, like they shared some sensory similarities. And the best thing about this after this classification was that the model managed to identify previously unknown relationships, which is what you want from statistics, to give you information that you did not know before, and between growth conditions and taste profiles. So we find several different things, like just relying on mathematical scores, like the silhouette coefficient and rand indices and purity and all of that. That does not guarantee that what you're finding is practically relevant. You have to you cannot rely completely on just the math of your data to get good results. You need to have domain expertise. You need to plot it out and see whether what you are seeing actually makes sense. And also distance-based matrix. If you have very high dimensional data, so if you have 20 attributes, 30 attributes, 1,000 attributes, if you're working with, say, for example, genetic data, you'll have 50,000 attributes because each of them have different genetic profiles. So again, these very, very high dimensional approaches, some of your standard metrics like Euclidean distance or whatever are going to collapse. They're not going to give you good results. So you have to look at the data and you have to look at your cluster results like very critically. Every time you see the first time you run a cluster analysis, you have to think that, okay, this is completely wrong. And what can I do to improve it? Even if it ends up correct, you have to be very, very critical. And and so it is very important that you evaluate these clusters against criteria beyond just math, beyond just statistics. So like you trust in your domain experts, you trust in your gut sense, and you look at the data very, very critically. And these are three different examples of like cluster analysis. where something very small went wrong. So in the first one, what people were doing were medical image segmentation. So you take an image of, like, say, a chest X-ray or an MRI result or something like that, and you segment it according to different like features within that image, right? So what happens? This is a very common. Like, you will find like a bunch of different PhDs in the computer science department is working on some variation of medical image segmentation with expert annotation. Expert annotation means that, like, a doctor or a technician or a nurse has actually annotated the data, like the X-ray or the MRI results or whatever, and they have said, okay, this is what we are seeing. These are like anomalies. These are like regular stuff. This is what it should be. This is what we are seeing. Things like that. So people have annotated it. But what happened in this case is that in this particular paper was that the algorithm was getting much better inter-rater agreement than the human experts. So inter-rater agreement is as the name suggests, it's like you have different rating, different algorithms or different methods or different people who are rating a set of data. And inter-rater agreement means, are all of these people or are all of these agreements agreeing with each other? Are they reliable across different rating schemes or understanding schemes? So what the problem what we are getting is that the human experts which we were validating against had very systematic biases. So they were making a single mistake, but everyone was making that same mistake. That's what is known by systematic biases, as opposed to unsystematic or random bias. So systematic bias means that everyone, like all the humans that had done the annotations, had made some mistakes, and because of that, like our actual results were very far from the real world. So what does that mean? It means that, like, even if you rely completely on domain experts or expert validation, if that expert validation itself is wrong, then you're completely stuck, because your entire model is only as good as your ground truth. So if your ground truth itself is wrong, then it is out of your control to improve it purely using math. Like, you might find like underlying truth sometimes that contradict the ground truth, but again, then you don't know what is correct. Is your math correct? Is the ground truth correct? So again, these are challenging things that if you're working on real world data sets, you will have to deal with. There are solutions for it, like in the paper that I'm talking about, they did ensemble validation. Ensemble validation means they brought in different experts and they brought in different rating schemes, and they combined all of them together to find better consensus and to find much better agreement to overcome these systematic biases. But these are heavily field dependent. Depends on exactly what model you're trying to solve and what cluster you're trying to find. The second one is what it created the problem with, like, very high dimensional data. So what they were doing is gene expression clustering in cancer research. So they were trying to figure out which genes were indicative of certain different types of cancer. In any kind of gene analysis, if you're not using like standard genetic analysis tools, you will find the big problem is that they are very high dimensional data. Like it says here, there were 20,000 plus genes, and so the entire dimensions of the set of attributes of the data was like 20,000. So you can imagine there are 20,000 columns, not just rows. There were 20,000 columns. And so the standard distance-based validity, so like when you're trying to calculate what is the distance between two different clusters, or if you're trying to calculate the distance between individual points within clusters, your this distance concentration error means all of them are going to collapse into single values. Like all the distance measures that you take, because there are so many different dimensions, the result, the distance that you get are meaningless, essentially. So the way to solve this is well, there are multiple ways. One of the ways is to reduce dimensionality using PCA or using any other dimensionality reduction method, or you find like lower dimensional, just you find a couple of like lower dimensional attributes that are more representative of the entire data set, and you calculate your distance metrics within that lower dimensional dashboard. Again, the results may vary. It depends on what you exactly you're trying to do. And the third example is something I've personally dealt with. So anomaly detection for network security means that you have, say, for example, you're a big ISP and you have millions and millions of connections that you're handling. How do you distinguish a malicious connection? How do you distinguish between, say, someone who's DDoSing, like someone who's performing a distributed denial of service attack against a single node? How do you distinguish that between the other millions and millions of different connections that are constantly going on? So anomaly detection is a very complicated task, and ISPs and like lower level bandwidth providers are constantly dealing with this. So this particular paper that I'm talking about, what they found was that they designed a new system for collecting information. This is an example of the paper that I'm talking about. This is by Migrate. I think this tool is called Netflow Analyzer. So this paper came out of this tool essentially. So what happened was that like no matter what cluster validity analysis they were using, they were all giving the wrong results. So what happened in this case was something that you would not see in your exams or in textbooks. What happened is that the entire data set from just one cluster. So there were no multiple clustering. So everything within the area of interest could be combined and fell into one cluster. So all the cluster metrics failed because this is an edge case that they hadn't considered, because the minimum number of clusters for a lot of these cluster analysis tools that we'll talk about just after this requires at least two clusters. So if your entire data set falls within a single dominant cluster with just a couple of outliers which don't form clusters on their own, your metrics are going to fail. So you have to figure out like asymmetric validation metric to figure out to look at the actual data to figure out what's going. Right. So again, these are all examples, real world examples of why we need to do cluster validity analysis and why it is easier and harder in different conditions. So now let's talk about, now let's go into like actual cluster analysis and okay, and some of the terms and attributes that we talk about. So measuring the quality of the clusters that we were talking about, initially the very fundamental metric that we use is a dissimilarity or similarity metric, and which is expressed in the terms of a distance function. And a distance function in a Cartesian plane essentially means how far two different clusters are from each other within that Cartesian plane. Essentially, like that. This is not the goodness metric. So just the distance function alone won't tell you any higher order information about the clusters. So there are separate functions that is going to use this distance function to calculate how good a cluster is. Right. So and for different types of data, you need obviously very different types of distance functions. For Boolean data, for category. For Boolean data, if you use a standard Euclidean distance function, it's not going to make any sense because the distance is going to be fixed, right? For categorical data, distance has no meaning, right? So if you have multiple different categories, if your categories are purple and blue, then there is no metric for distance between purple and blue. I mean, you could have language metrics between them, but obviously that's not how distance works. For ordinal and ratio variables, for interval scale variables. So again, for different types of variables, you need different types of distance functions. You also have to assign weights to different attributes or different variables based on both the data semantics and based on your expert knowledge or domain knowledge. And again, all of this is very, very subjective. Like you can get, like I showed in the example, the wine example earlier, You can get high scores for some of these metrics, like whether it's silhouette scores or NMI scores or whatever. But that alone doesn't really tell you. And a big challenge is that if you have done one set of clustering and then you do another set of clustering, and one has a silhouette score of 0.8 and another has a silhouette score of 0.5, you cannot compare them. That there is no comparable information between those two. You cannot directly say that, okay, this clustering is better than this clustering because it depends on so many different subjective things. So yeah, that's so. Uh, the fundamental thing for clustering is that we try to minimize intra-cluster distance and maximize inter-cluster. So this is very obvious. Like if you are trying to find out whether your cluster is good or not, then obviously the more closely packed the individual clusters are, the better it is, and the further away they are from other clusters, the better it is. Right. So this is very obvious, but this is if you take a data set and you look at it like practically, and then you look at your cluster practically, this is the best way to compare how whether your clusters are working or not. Right. So look at them, see if they are separated clearly. If you can put a hyperplane between them, then it's really good. That's called SVM. And even if you can't put a hyperplane between them, it may or may not be good. Again, it depends upon domain knowledge. Uh, this is what I just said. A good clustering requires very high inter-class similarity and very low inter-class similarity. And the quality of this result, of the clustering result that we're talking about, depends upon which similarity measure you have used, how you have used that particular similarity measure, and whether using all of these similarity measures, all these indices and all these statistics, are you able to find any deeper truths from the data, right? Because if all you can find from all your analysis is what is already visible, then your analysis is not very useful. So again, the goal of your analysis, the goal of all data science is to find truths that are not obvious. So that's what your clustering metric is trying to find out. So these are again, this is a summary slide of all that we have talked about. So a good clustering technique means it has to be scalable. So if there are 2 dimensions versus 20,000 dimensions, it should work in both cases. It should be able to deal with different types of attributes with any shape. So you're in real world, things are not going to be perfectly Euclidean. They're not going to be perfect circle. They're going to be weird, very, very, very weird shapes. So it has to be able to deal with all of them. You need to have some amount of domain knowledge to figure out like what you are seeing makes any sense or not. You have to have some ability to deal with outlier points, noise points. It has to be insensitive to order of input records. So even if you shuffle the input data, your clustering shouldn't change. Right. That's what it means by it should be insensitive to the order of input. So if you shuffle your input data, or if you perform any n-fold separation within of the data, the cluster results should remain broadly the same. And then your results should be interpretable, they should be usable, etc., etc. So the first 2 things we're going to talk about are unsupervised cluster validity analysis, and then we're going to talk about supervised. For unsupervised, what we mean is that all we need to evaluate how good our clusters are is what is within the clusters themselves. So we have to consider how much the clusters are separated and how compact these clusters are. There are a bunch of indices that does that, but silhouette coefficient is the easiest. And it's honestly simple enough that it can be done very fast on very large dimensional or very large data set. And you should be able to do this by hand, essentially. Silhouette coefficient requires 2 small different things. One is cohesion, and the other is separation. Cohesion is measured by within cluster sum of squares. So WSS stands for within sum of squares, and separation measures the distance between the different clusters. So between cluster sum of squares. And sum of SSE is what's up? Yeah, yeah, that's pretty much what cohesion and separation is. That's that's why these are like for any sort of unsupervised cluster analysis. These are the fundamentals. Like for it's used by silhouette coefficients, but it's also used by all the other coefficients that you might find on different papers. Right. So and because these variations, BSS plus WSS is going to be a constant value, which is the SSE. The cohesion measure is called the sum of squared error, which you have all probably heard of, which is root over the error squared. So essentially, it makes it eliminates modulus errors between clusters. So BSS and WSS are what we're going to be using to find for the silhouette coefficient. Here's a good example of how cohesion is calculated, the individual points within a cluster, and how separation is calculated. So which is each point within one cluster compared to each point within another cluster. That's what WSS stands for here, as you can see. So here CI, modulus of CI stands for the size of each cluster, the size of cluster I. So silhouette coefficient, it combines cohesion and separation. So it checks how much you have been able to minimize intercluster distance and how much you have been able to maximize intracluster difference. So the silhouette coefficient, you have to calculate two different values. One is the average distance of I to the points within its own cluster, and then the minimum of the average distance of that point to points in another cluster, essentially. And so the silhouette coefficient of the individual point is 1 minus A over B if A is smaller than B, and the inverse of that. So B over A minus 1 if A is greater than B, which doesn't happen because it's very obvious, right? If you're getting the second case, that is individual clusters are very broad and like very flattened out, and the clusters are very close together, which generally means if you're hitting the second case, something has probably gone wrong in your clustering method, or there is no like underlying cluster in your data. That is also possible. If you have truly random, if you take random noise and you cluster it, you will hit the second case in the silhouette coefficient. The value is mostly it falls between 0 and 1, obviously because you're subtracting 1 minus A over B. And the closer you get to 1, the better it usually is. But like I said, gave you a counter example in the wine example, where even though the silhouette coefficient was very close to 1, the actual clusters were pretty bad. So again, you have to rely on domain knowledge to figure it out. A good thing about silhouette coefficient is that what people usually use it for is when you're doing k-means clustering, you start off with some arbitrary value of k-means clustering, like you start off with k equals 3 or 2 or 5 or whatever. Then you compute the silhouette coefficient, and you use that value to shift your k. So you shift it up or down based on what your silhouette coefficient is. So it's a correction metric. It can also be done like you'll find that there are libraries within sklearn, the Python sklearn library, that does this automatically for you. So based on your silhouette score, it's going to shift your k-means k value up or down to optimize for the silhouette score. Again, that's something you have to look at the data itself to figure out if what they're doing is good or bad. If a silhouette value is +1, that means the sample is it is a perfect sample. So it's very far away, like essentially infinite distance from its closest, because it has to be infinite distance because A over B this has to become 0 for silhouette coefficient to be 1. And so that means it's infinitely far away. And so, but it should, as it approaches 1, the clusters are more and more separated. And a value of -1 means the clusters are more and more diffuse. We usually use a distance matrix to calculate this because in the real world, you have like thousands of clusters and thousands of data points. But you can do it by hand if it's like 5 or 10 or 15. But more than that, you need the distance matrix and the incidence matrix to compute the correlation between them. Again, if you have very high correlation between in the distance matrix, then your clustering is good, as is obvious. This is the standard distance matrix correlation. This is a standard correlation formula, just modified to work with a distance matrix and an incidence matrix. This is not very useful for you because nobody does this by hand. But again, it's there just so that you know what a distance matrix and an incidence matrix is. So this is an example of taking random points. So this is pretty much spread out over the coordinate block, over the axis randomly. But if you use different types of clustering, you'll find that this is creating some random cluster, right? I would say, in my opinion, DBScan does the best job, but because these points are random, none of them are actually doing a good job because there is no cluster in the underlying data, right? So DBScan is able to point out that like this and this are outliers, and that top block is a cluster, while k-means, depending upon even though DBScan and k-means both have 3 clusters each, the k-means clusters are not very good in this case, and the linked clusters are pretty bad. So again, this is I would personally say there are no clusters in this data, but if there were, DBScan is probably the closest to approach like real world clustering. But again, this is why you need to look at the underlying data. And if you look at the data, you see that this is pretty much random. Like, what information can you possibly gain by clustering this data, right? It doesn't tell you anything. So, but compare that to this data, right? So this is where the correlation matrices, the correlation metrics come out. So like this is very obviously clustered, and this is very unobviously clustered. But even still, the correlation value it gives you is close to 60%. So again, the statistics and math is not all there is. You have to look at it with your own eyes. You have to judge it using your gut instinct to figure out any of the seed sets. So let's. I mean, this is how you calculate essentially the distance, and this is how you end up calculating the silhouette scores. So if you have 3 clusters, and the points have been given there, and because this is very low dimensional, right? This is just 2-dimensional. So the standard Euclidean distance metric works perfectly fine in this case. If this was like 10,000 points per set, then this would be correct. So take a random point in cluster 1. So first point in cluster 1, and then you calculate the average distance from that point to all other points within that one cluster. So you calculate the distance from 1, 0 to 1, 1, and you find the average distance, because there's just 2 points, the average distance is just 1. So the average distance from cluster 1 is 1. So that's the value of A. So you have the average distance of I to the points in its own cluster. So the value of A in this case is 1. But you have to calculate B, which is the value of this cluster distance, average distance from this point to all the other points. So you do that as well. This is very simple calculation. Calculate distance from 1, 0 to 1, 2 to 2, 3 to 2, 2 to 1, 2, and you find the distances, and then you divide the distance by 4 because we are calculating the average. So the average distance from the point 1, 0 to cluster 2 is 2.325. And then the average distance from point 1, 0 to cluster 3 is calculated is 2.7. So since 2.325 is smaller than 2.7, the minimum average. Let me move this before I. So the minimum average is 0.325. Why are we taking the minimum? Because look at the formula for silhouette. B is minimum of the average distance of I to the points in another cluster. Right. So this is very simple. Put the formula here instead of doing this thing. Oh, formula is here, right? So the silhouette coefficient of cluster one, A is 1, B is 2.325 because you're looking for the minimum. So you're using the first case, which is 1 minus A over B, and the value is 0.5699. That is your silhouette coefficient, and the silhouette coefficient of almost 60% tells you nothing, essentially. So this is practically useless, but you have to look at the data to figure out what any of this means. So again, you can do this for other points, other individual points in cluster 2 and cluster 3 as well. And the cluster with the highest silhouette coefficient is the best. So what you did here with cluster 1 point in cluster 1, you also do this with a random point in cluster 2, and you do this with a random point in cluster 3. So you run this calculation run this calculation 3 times, and the cluster with the highest silhouette score is the best cluster as far. What and you might be thinking, why is it called silhouette score? What does the word silhouette have for any of this? Essentially, what you're calculating is the shadow of that one point on all the other points. So that's now it's called silhouette because you see, for example, you're calculating the silhouette score of this cluster, right? So what you are doing is you're taking this point and you're calculating how much of if you're pointing a light at this point itself and it is hitting these other clusters, how much is it being shaded by that point? That's practically what silhouette score tells. Like how much of those clusters are being shaded by these points. So that's why it's called the silhouette score. And okay, for more cluster validity analysis, so you can also calculate cohesion and separation. But to do cohesion and separation, you need to know the centroids. So the centroids for each of, if you know the centroids for each of those points, you can calculate cohesion and separation. Formula is very simple. It's a simple subtraction and squared. It's SSE, so it's sum of squared of error. So you take each of the points, say for example in cluster 1, and you subtract it from the centroid of that cluster, and you square it. And so for cohesion of 1, it's 0.5, and for separation between clusters, you do it. You have to do 3 times, right? So you have to do cluster 1 to cluster 2, 1 to 3, and 2 to 3, and you calculate that is the sum of squared of error of the centroids of centroid 1 and centroid 2. You do this 3 times, and you get the separation value. For cohesion, you want small values because you're trying to minimize the intercluster distance, and for separation, you want very high values because you're trying to maximize the intercluster distance. And for silhouette scores, if you have very low cohesion and very high separation, then your silhouette scores are going to be pulled up. They're obviously going to be high. So this is how, in general, silhouette scores work, and this is why it's something you can pretty easily calculate by hand, because the calculations are pretty simple, and all that you need to do this calculation is just the values of this cluster 1 and cluster 2 and cluster 3. That's it. That's all we need. That's how you find the centroids. For sklearn.metrics, the Python library, scikit-learn, it obviously has silhouette scores. It calculates silhouette scores given this is how you do it. There's probably a practice or a lab for this. I don't remember exactly, but again, this is very simple. And like I said, you don't just do this. You don't just calculate Silhouette score and say like, okay, my work is done. You then look at the cluster itself, then you look at the data itself, and then you look at literature to figure out what the data is trying to tell you, and then you try to guess whether your work is good or bad, essentially. So don't just rely on the math. You have to think. Right. Now that we have done unsupervised clustering, let's move on to supervised clustering, which is the final two things that we'll be doing today. Okay, we have time. So today we'll be doing two different types of supervised cluster validity metrics. There are lots more. We'll be doing purity, we'll be doing normalized mutual information, and we'll be doing RAND index. RAND index uses something that you've already done previously, which is F1 scores. So true positive, true negative, false positive, false negative. So your precision recall metrics are going to be used to calculate the RAND index. What the RAND index does is, I'll talk about it when it comes up. So purity and normalized mutual information are both somewhat math heavy. Purity is fairly simple, but normalized mutual information is pretty complicated. We're not going to talk about like all the details of where it came up with, what it came up from. But an interesting part is if you have heard of Claude Shannon of Shannon entropy, like a very famous scientist, mathematician, statistician in the field of information theory, the field of entropy, Claude Shannon. He's the one who came up with the mutual information metric. And it is mutual information metric is widely used if you're doing machine learning, if you're doing AI. Mutual information is something you're going to come up, you're going to hit all the time. So now you will have a couple of in-class problems with purity, and you should be able to submit it online. There's something on the canvas that should already be available. So for entropy, for normalized information, and for purity, normalized mutual information purity, you have to know a couple of different terms. One is C of K, which is the number of objects in the kth cluster of the clustering solution. It's obvious. And P of J is the number of objects in the cluster of the ground truth. So because this is supervised clustering, you have a ground truth. You know what the cluster results should look like. So that means P of J is what's the true results, so to speak. And C of K is what your model is, what your clustering solution has come up with. So obviously, to understand whether your cluster analysis is good or bad, you have to compare your work, which is C of K, with the real results, which is P of J. And the way we do that is the intersection between C of K and P of J is what we're looking at here. In this figure, I copied this straight from Wikipedia. So it says X and Y here, but those are C and P. H here is entropy and I is information, right? So purity is very simple. It's 1 over n, where n is the total number of points, and you sum the maximum number of points in each cluster that's correct. So if you look at the cluster that your model has given you, you find out which point is most highly represented within that cluster. So compare it to the real cluster, and you take that maximum value and you sum it up for each of the different clusters. It'll be easier to understand once I show you some example. So normalized mutual information is you find first the mutual information, which is I of C and P, where C is the number of clusters that you have found and P is the count of the cluster. And you normalize it by the entropy of each of them. So the square root of H of C and H of P is a normalization factor, 1 over this. What is I of C of P is this. It's if you have studied probability density functions, this is an expansion of a PDF. That's what this is. There are many, there's a lot of difficult math behind it, so which you don't have to worry about right now. But what you have to know, what you have to be very careful about is that this is, because this is a summation and not an integration, this is for discrete variables only, not for continuous variables. So if your data, if whatever you're trying to answer is a continuous variable, this will become an integration, not a summation. So keep that in mind. As is similar for any probability density function, which should be obvious. And this is the standard term for entropy, which you have probably already learned in your previous classes because it's already in your exams. So this is the entropy of your cluster results, and this is the entropy of the ground truth. So let's look at how purity is calculated. What's up?
So why does summation not work for continuous in this case?
Well, for continuous means, okay, so you know how integration works, right? So integration assumes that there are no, that the variable that you're integrating is differentiable at all points. So it is a continuous variable. If it is a discrete variable, if you integrate it, then the gaps between those discrete variables are also going to be summed up. So you cannot integrate a discrete variable. You sum up a discrete variable, but the continuous variable you integrate. That's by the fundamental property of calculus, that it has to be continuous. Because if there's any gap, then your integration formula is going to fail, because it's not differentiable at all points. Okay, so let's calculate purity for this function, right? So again, this is very simple, right? So it says X and O because that is the ground truth. We know that these points, the X points are from one class and the O points are from a different class. But your cluster has combined them together. So for purity, you can see the formula for purity is the maximum of the intersection between between what your cluster has created as classified as points and what is the ground truth. So that means there are 1, 2, 3, 4, 5 points that fall that are in this intersection. Does that make sense to you? Because those 5 points are within a cluster, and the ground truth itself also tells you that they should be within a cluster. So that means in this case, the value of this is 5. Right. For this one, it's 1, 2, 3, 4. So 4 circles should be 4. And in this case, there are 1, 2, 3 rhombuses. So there are 3 rhombuses. So in this case, the majority class and the number of members of the majority class for the cluster are for cluster 1, it's 5. For cluster 2, it's 4. And for cluster 3, it's 3. So purity is 1 over n, where n is the total number of points, it's 17 points. 1 over n times the sum of 5 plus 4 plus 3. So purity is 0.71. Okay. It's a very simple score. It's a very simple method of calculation. So you should be able to do it pretty easily. So the other index that I was talking about is the normalized mutual index, which is NMI, which is a pretty good measure for determining how good your clustering is. It is a form of supervised clustering because we need the class labels. We need to know the ground truth, and because now this is a very important point. This is normalized. So normalized means we get an NMI result for different types of clustering, and then we can compare them. This is not true for purity. This is not true for silhouette coefficient because none of them are normalized. So what this means is that if you have used clustering results for 2 different data sets or for 2 different models, and you have been given some purity score or you have been given some silhouette score, you cannot directly compare them because they're not normalized against each other. It doesn't make sense to compare high purity, 2 different high purity scores. But NMI is normalized, so you can compare them. And this is one of the most fundamental ways of figuring out if you have like a benchmark data set and you want to see whether your new clustering method that you have come up with is good or not, you use NMI. Well, you use some form of mutual information. Doesn't have to be this particular form of normalized mutual information, but you use some normalized method. So yeah, this is what I mean by like in the ground truth, 1, 2, 3 falls within one cluster and 4, 5, 6 falls within another cluster. And in the actual clustering result that we have gotten, 2 is like a completely wrong cluster. So let's see how NMI works to compare it. So for normalized mutual information, um, forget the old the formula that I showed you. This is a simplified version of that formula, right? So you need 3 different things essentially. You need the entropy for both the original cluster and the ground truth, and you need the mutual information between the original cluster and the ground truth. So in this case, Y is your cluster and C are the original cluster. It's the ground truth. So let's do this for this particular example, right? So in this case, the ground truth is labeled by the shape of the points. So the stars are one cluster, the squares are another cluster, and the triangles are another cluster. But in actuality, this is what your cluster results have given you. So let's calculate NMI. So the first thing we have to do is we have to calculate the entropy for the original clustering, like for the ground truth clustering, which is done like before you even start your own clustering, right? So you use the standard entropy formula. So 1 over n of 1 over n, and you sum them up and you invert it. So it's negative of sum of all of them. And so this is essentially the entropy. So for P, Y equals 1, how many points there are? So 1 is like star, or 2 is circle, 2 is triangle, and 3 is square or whatever. It doesn't matter. The values should have been here. For some reason, they haven't shown up. Whatever, doesn't matter. So this is the standard way of calculating entropy. So you calculate the entropy of the original data set before you even start clustering, right? And then you calculate the entropy of your cluster. So for C equals 1 and C equals 2, you calculate the probability of how much they are correct, and you do this every time you cluster. So these are the actual results of your clustering. And so mutual information is entropy of the originals minus the entropy of your clustering results given the ground truth information. So this mutual. So what this tells you is that this is pre-normalization. So this is mutual information. So this mutual information tells us how much the entropy of the class tables have been reduced if we know the cluster tables, right? This formula should be familiar to you because you have done decision trees, and this is very similar to information gain within decision trees. So in cluster 1, there are 3 triangles in cluster 1. And there are 3 rectangles in cluster 1 and 4 stars in cluster 1. So you calculate the conditional entropy using this formula, and you get this value. And you do the same for cluster 2 using the same conditional formula. You calculate the same conditional entropy, and finally the mutual information is 1.5, which we already calculated as the entropy of that, and then you add up these 2 entropies, and so this is the normalized mutualized information. So this upper value, this is the mutual information, and 2 over HY plus H of C is the normalization index. And based on that, we find the NMI value of 0.1089, which is pretty low. Again, this is very easily calculated using sklearn. There are normalized mutual information score is a function to use. And if you give perfect labels, the output is going to be 1. And if you give completely imperfect level, so where all the values are completely wrong, then you get an output of 0. This is your in-class information, in-class assignment. See if you can calculate the NMI. Right. This should be, you can try and do it now. This should be up till 6 o'clock today. So if you want, you can finish it up to 6 o'clock. I can give you, how much time do you have? I can give you 5 minutes to do this. If you want to try to do it now. This is not very complicated. This is just simply what we just did right now. This normalized information. So you have to calculate all these 3 things, right? So you have to calculate the information gain. You have to calculate the entropy of Y. To calculate the entropy of C. Essentially, these are the 3 things that you have to calculate. So how do you do that? You have this value. You have to calculate the entropy of Y, calculate the entropy of C, that goes into the denominator, and then you calculate H of Y there, which is conditional entropy, but the idea of this particular formula for each class. I tried to, I mean, again, this is up on Canvas, so you can download the slide and look at it yourself and do it. But you have till 6 o'clock to do it.
And we're getting points.
You will get points.
What is points?
It's normal grading points. Like a standard in-class stuff. If you think you want to do it after class, then that's fine with me as well. But if you do it now, it just saves you time. Not very fun. And the solution is like just after this. There's slide after this, and show you the solution anyway. So it's just to see if you can, because this is one of the things that is probably very likely to come up in your final exams. So it's good if you're able to solve this. So again, go step by step. Right. Calculate the entropy of the count root. Calculate the entropy of the real cluster results. Then you can calculate the conditional entropy and then put it in the formula. That's it.
So which PowerPoint are we on?
Cluster validity. It's going to be slightly different because the early example slides that I put in are not there. So the rest of it is Dr. Rizk slide, but I'll put it up. The first thing is you calculate the entropy of the count root. So you count how many squares are blue out of all the, like, how many points are blue squares out of all of them, how many points are red triangles out of all of them, and how many points are stars out of all of them. Right. So those are the 3. So you calculate that first, then you calculate the entropy. So it's 1, 2, 3, 4, 5, 6, 7, 10. So 10 out of 20 are blue, and 5 out of 20 are red, and 5 out of 20 are red. So this is the exact same as the example. So the entropy of what's up? It should be there should be an in-class submission on Canvas. Oh, well, I'll take a look. I forgot to make it online or whatever. Keep working on this and I'll see what I can do. Modules in class. Neural network. Okay, it should be called silhouette for some odd reason. Okay, it should be up. It's called silhouette. Submit it in the module called silhouette. That's where you should submit it. No idea where it's called silhouette. Okay. Having trouble again. First things first, this remains the exact same, but you can do it again on your own. You first find the entropy of the class tables, then you find the entropy of the class itself for the two different clusters, which is how many points are there in each cluster, right? So how many points are there here? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 and 10. So the h of c and h of y remains the same. But the conditional probability is what changes. So both h of y and h of c in the given example versus here remains the exact same. But this part, the mutual information, is what's going to change. So this conditional entropy is what's going to change. So this is what you have to do on your own.
But I'm not seeing any stars in the first cluster.
Yes. In this case, there were stars in the old example, but in the actual example, in the actual in class, there aren't any stars. So it's different. So in this case, you see there are no stars here. Yeah. So this is the one you're trying to solve. So there are no stars here. So that it becomes 0 out of 10. And it becomes 1, 2, 3, 4, 5, 6, 7. 7 out of 1, 0 out of 10, 7 out of 10, 3 out of 10. So that's what you're using for this. So it's 0 out of 10, 3 out of 10, and 7 out of 10. So you're calculating the conditional entropy given this. And 0 log 0 you consider as 0 for your calculation. So this is, you do this for cluster 1, and then for cluster 2, in the old example, it was 2, 7, and 1. In the current example, it's 2, 5, and 3. So you calculate this conditional entropy as well. For it remains the exact same, just instead of 2, 7, and 1, it's 2, 3, and 5. That's it. So once you have that, you can calculate this. Becomes 1.5 minus the two mutual information values that you just calculated, and then you calculate this. Let me know if you're stuck.
So we just put in the NMI.
Yes.
Yep. By the way, just how did we get the 1.5 and 1? Is 1.5 that like mutual?
Yes, so the formula is, you can see here what the formula is, right? So this is the formula, right? So you're adding the entropy of the class label plus the entropy of the ground truth. So
Oh, okay.
that's 1.5 is the entropy of the uh, class label, and 1 is the entropy of the ground truth.
Okay.
So this is the formula that you're using for NMR. That's the.
Will that always be 1.5 and 1?
No, it's,
Yeah.
it's 1.5 because here it's 10 out of 20, and again 10 out of 20.
Oh, okay. Yeah. And since it's the same thing, okay.
It
So
didn't change. Yeah.
Okay.
Because there were in the previous example there were 10 and 10 values. In this example, there's also 10 and 10. So that's why it's the same.
Thank you.
Okay, I'll give it another minute and then we'll move on.
License.
Yeah.
And once I get this, as what's subtracted.
Now we use this formula. So this is the two that we got is the two values in the bracket. This will be 1.5 minus and then put it in that's 2 times that value. You'll have it by 1.
What is the range of values that we expect from this process? Is it usually 0 and 1?
It's normalized, so it's between 0 and 1.
Excellent.
This many again?
It shouldn't be called silhouette. I think there was supposed to be a class for the silhouette score as well. That got removed, so it's still called silhouette score. Okay, I'll move on, and if you have time, I think this is open till 6 o'clock in the evening, so you should be able to submit it then by then. I'll discuss the solution right now anyway, so not a big problem. So again, this is entirely possible that you're going to get either this or silhouette score or purity as part of your final exam. So make sure you know how to do this. This formula is all you need, like this formula and this formula. So make sure you know how that works. So what we did is in the first case, we had 3 red triangles and 7 blue squares. So it's 3 out of 10, 7 out of 10, and 0 out of 10. So the conditional entropy is 0.44. For the second case, it's 2, 3, 5. So the conditional entropy is 0.74. So we add them up and we subtract it from the conditional. This got messed up, whatever. So we subtract it from the entropy of the ground truth, and then we get the normalized mutual index of 0.2533. This is slightly better because these clusters are slightly, I don't know, slightly more clustered. You can calculate purity the exact same way. Like I said, in this case, it's 1, 2, 3, 4, 5. So it's 5 red, and the next one is 4 blue, next one is 3 green. So you can use that to calculate the purity of individual clusters, and then you can use it. The total purity is the formula that I showed you earlier today, which is you add up the total number of points here. So it's 1, 2, 3, 4, 5, 6. 6 plus 1, 2, 3, 12, 13, 14, 15, 16, 17. So there are 17 points or total. So it'll be 1 over 17 times sum of 5 plus 4 plus 3. So it's 12. So it's 12 by 17 would be your total purity in this case. So it's as easy as that. So you can calculate individual purity, but the problem with this is, again, this is not normalized. So you cannot compare purity values between different clusters to give you better results. So this is the fundamental difference between extrinsic and intrinsic, or supervised or unsupervised clustering. Supervised clustering, you're comparing your cluster to an actual ground truth. So these colors are your ground truth. If this were unsupervised, you wouldn't have these colors. So that's when you would be using your silhouette coefficients and your distance metrics and all of that to calculate the quality. So the quality measures for supervised are purity, precision, recall, NMI, and for unsupervised, it's silhouette coefficient. There's also RAND index. This you can study on your own. This is not going to be in your final exam, but RAND index is essentially a method of checking whether how similar two different clusters are. Right. So that's how similar two different clustering methods are. So if you have used method A, if you have used k-means to cluster one data set, and if you have used dbScan to cluster another data set, then you will use RAND index, RI, to calculate which of them gave you better results. And this is only used for supervised because you take the results of these two different clustering methods and you compare them to the ground truth to see which of these clustering methods have given you better results. So that's why you use a precision score and recall score and F1 scores that you have learned earlier. So so the RAND index is essentially just this: true positive plus true negative divided by the entire data set, true positive plus false positive plus false negative plus true negative. And so what RAND index essentially tells you is that it's very basic. It just tells you what fraction of your entire clustering result is correct, in that it matches the ground truth. Now, again, as the example I showed you earlier in the class tells you, your ground truth may or may not be correct. Your results may or may not approximate the ground truth enough, or if it might approximate another different method that approximates it less, might be better, might be worse. Again, these are all very, very subjective. So that's how RAND index works. And the way to calculate it gets somewhat very complicated because every time you do it, you have to calculate this metric data, the true positive, false negative, false positive, false negative data. So once you have that calculated, take the RAND index is very simple. And it's very easy to do it in Python as well. Because again, this true positive, false positive, true negative, false negative is very easy to calculate. So that's it for today. If you have any questions, you can email me, talk to me on Teams. Your final exams, your exam 2 is still being graded. I'm like 80% done. There's like 20-ish left. Your scores are better than exam 1. I've been as lenient as possible. So your grades are going to be out this weekend, possibly, if a doctor is taken. Good luck and submit your in-class to that silhouette.